Today in this video we're going to look at section 9.6, which covers solving rational equations, and this is going to be the first part of two videos. Some prerequisite knowledge you'll need before watching this video. Make sure we understand how to simplify, multiply, divide, add and subtract rational expressions, all topics we covered prior to spring break. And what we're going to look at today particularly is when we have a rational expression equal to another rational expression. The nice thing about these problems is they're very similar to what you learned in pre-algebra and algebra 1 with ratios and proportions. So, if we have 5 over 2x subtract 2 is equal to 15 over x squared subtract 1, it's just like we have a fraction equals a fraction, which you guys have learned in the past. All you have to do to solve is cross multiply. If you cross multiply, you no longer have any fractions. So let's start with 5 times x squared subtract 1. That's going to give us 5x squared subtract 5. And when we multiply 15 times 2x subtract 2, we'll end up with 30x subtract 30. Remember, it's almost like you're distributing. The 15 needs to get multiplied into both terms. Same thing with the 5. Well, now we have a quadratic, which we know we have to get everything to one side. So I'm going to move the 30x over by subtraction, the 30 over by addition. And now we should notice that we have a quadratic where all the terms are divisible by 5. So we can go ahead and factor out a 5. And we can go ahead and divide that 5. And now we have a very easy quadratic to work with, one that is actually factorable. So we can factor this out to be x subtract 5, x subtract 1, and that will give us two answers, one of 5, and the other answer is 1. One thing you're going to want to make sure you do with rational equations is substitute your answers back into the original to make sure that they work. So let's start with the answer of 5. So we're going to take 5 and we're going to sub it in for x, and that means both sides of the equation should equal each other. So 2 times 5 is 10, subtract 2 is 8. So this first fraction is 5/8. If we do the same thing with the second fraction, 5 squared is 25. Subtract 1 gives you 24, but 15 over 24 will simplify to 5/8, which means the answer of 5 does work. Now, when we try to test out our answer of 1, one thing you're going to notice is, let me get rid of these since we're done with those, 2 times 1 is 2, but if you subtract 2, you end up with 0, and we know 5 divided by 0 is undefined, which can't happen. And over here, the same thing will occur. 1 squared is 1, subtract 1 is also 0. Even though we have undefined equals undefined, this answer is still not going to work. It's going to be an extraneous solution because you are not allowed to have a denominator of 0 in a fraction. Okay? So our only answer in this problem that works is 5. Now we can try this one, which looks like it's going to be a little bit easier. There's no squares anywhere with our variables, which means we're most likely not going to deal with quadratics. So once again, we're going to cross multiply to solve. So we'll start with the negative 4. Negative 4 times x plus 2 is going to be negative 4x subtract 8. 3 times 5x plus 10 will give us 15x plus 30. So now we have a nice easy linear equation to solve. I'll bring my 4x over by addition, the 30 over by subtraction, which will then give us an answer of negative 2. So this time we only have one answer, but once again, we're still going to want to check this answer to make sure that it works in the original equation. Okay? Once you sub negative 2 in for x, this is going to end up being negative 10 plus 10, which will make this first fraction undefined. And the same thing is going to happen in the second fraction. So in this problem, the only answer we have does not work, which means our final answer to the problem is no solution. The only answer we actually arrived at ended up being extraneous, so this problem has no solutions, which means there's no x value we can sub into either side of the equation to ever make these two sides equal to each other. Okay, so the last two problems we're going to look at in this video are going to be application problems. And some key things we're going to need to look at prior to doing these is we're going to use the formula D equals RT in the next two problems. Most of us should be familiar with this if we've taken physics or some other science classes, but if this is new, what these three variables represent is d is distance, r is rate, and t is time. Your distance is always going to equal the product of your rate and time. If you're traveling 50 miles per hour for 2 hours, that means you traveled 100 miles. 50 times 2 is 100. So that's always going to remain true, so keep this in mind as we go through the next two problems. Okay, if you need to pause the video so you can write the problem down, please do so, because I am going to read through it and then go ahead and work through. So Rosa can jog 5 miles downhill the same time it takes her to jog 3 miles uphill. She jogs downhill 4 miles per hour faster than she jogs uphill. Find her jogging rate each way. It makes sense. We all know that we will run faster if we're going at the same rate. Downhill, we're going to go quicker than uphill because we have that extra advantage. So, in this particular problem, Rosa's going 4 miles per hour faster downhill. The key part of this problem, the key phrase, is where it says the same time. Okay? And what we can think about is her downhill time, we can call that T sub D for time downhill, is equal to her time uphill, T sub U. And you can use whatever subscript you want. T sub 1, T sub 2, whatever is going to help you kind of differentiate between the two. Okay? Well, the key thing we're going to use, I'm going to write this on the side, is the formula D equals RT. Distance equals rate times time. Well, since in this problem our times are equal to each other, we can manipulate this formula and isolate the time variable. Well, we can get t by itself by just dividing both sides by r. So what that means is time is the same thing as distance divided by rate. And since this is the setup of the problem, we're going to use this d over r to actually solve it. Even though the times are equal, nowhere in the problem does it actually give us that time. So this kind of doesn't help us out. So since t is the same thing as d over r, we can say her downhill distance over her downhill rate is equal to her uphill distance over her uphill rate. And I'm using the same subscript. We just know that d over r is the same thing as t. So now let's see if we can start filling in some of these variables from the problem. Well, Rosa can jog 5 miles downhill. Well, that's her downhill distance. 3 miles uphill. That's her uphill distance. Okay? Now, it doesn't actually give us all the rates, but it does give us a really important piece of information. She's going 4 miles per hour faster downhill than uphill. So since we don't know how fast she's going uphill, we can just use a variable, r or x or whatever variable you want to use. And since she's going faster this way, we can just say x plus 4. 4 miles per hour faster than this way. Now we have a very easy equation that looks like the previous two examples, and we can cross multiply to solve. Before I solve, let me just recap how I got this one more time. We know that the problem says the times were the same. So that's how we did T sub D is equal to T sub U. We rewrote our distance equals rate times time equation so we could isolate the T variable. So T is equal to D over R. And so all we did was change T to D over R in both. And then we took the information from the problem and substituted them in. So now when we cross multiply, 5 times x is going to give us 5x. 3 times x plus 4 is going to give us 3x plus 12. So when we solve this problem, we'll move the 3x over by subtraction, and we will go ahead and get x equals 6. Really important in these problems, we read what the problem's asking us to find. Find her jogging rate each way. Well, if we look at it, x equals 6. Well, x is representing her uphill rate. So we know when she's going uphill, she's going 6 miles per hour. We know that her downhill rate is 4 faster than her uphill. Well, 4 plus 6 is just 10, which means her downhill rate is 10 miles per hour. Okay? So, make sure when you're doing these problems, you read carefully of what the problem is asking for. An alternate way you could have also done this problem from this step, some people look at it as, well, the distances aren't going to change, but you could have thought as the downhill rate is x, and since she's going slower uphill, you could have also done x subtract 4. This is actually the same as this. We're just looking at it as x and x minus 4 instead of x and x plus 4. When you cross multiply this way, notice you're going to get some different numbers, but when you solve, your first answer is going to be 10. Because x is downhill, you get the downhill answer first, and then when you subtract 4, you get 6. So there are some different ways of setting these problems up depending on the way you're looking at it. Okay, why don't you guys go ahead and read and try this one, and then pause the video, and I will go ahead and put the answer up so you can see how you did. So Ryan can row a boat downstream 14 miles in the same time he can row upstream 8 miles. If Ryan rows 5 miles an hour in still water, what is the rate of the current? Once again, the key piece to this is same time. So a very similar situation as the last problem. His downstream time is equal to his upstream time. So we're really going to set this problem up the exact same way. We know distance is rate times time, and since we have times equal to each other, we're once again going to do t equals d over r. So Ryan's downhill distance over his downhill rate is equal to his uphill distance over his uphill rate. So if we go through the problem, we can see that his downstream distance is 14 miles and his upstream distance is 8 miles. Okay, now the difference in this problem is we don't know a lot about the rates, but we do know that Ryan rows 5 miles an hour in still water. So if there's no current, he's going to be going 5 miles per hour. Well, if he's downstream, he'll be going 5 miles an hour plus whatever the current is pushing him. 5 plus x. It's going to make him go faster than 5 miles per hour. Downstream, he's going 5 miles per hour, but he's getting current against him, which would be 5 minus x. So when Ryan's going uphill, he's going to be going slower than 5 miles per hour because the current is pushing against him. So once again, we can cross multiply to solve. So 14 times 5 is 70. 14 times negative x is negative 14x. If we cross multiply the other way, 8 times 5 is 40, and 8 times x is 8x. So if we go ahead and solve this equation, I can subtract the 40 from both sides and get 30, add the 14x to the other side, and get 22. So in this problem, we're not going to get a nice whole number answer, which is okay. If you think about rates of currents and speeds, a lot of times they're not going to come out nice whole numbers. But since we're talking about an actual current, this would be a good time to maybe use a calculator and estimate what our answer is going to be. So 30 divided by 22 gives us roughly 1.36 miles per hour. So in this problem, they don't want to know how fast Ryan's going each way. They just want the speed of the current. So the current was about 1.36 miles per hour. If they asked you what his speed was each way, then you would go ahead and sub 1.36 back in, add it to 5 for his downhill, or downstream, excuse me, and 5 subtract that for his upstream.